Hello, everybody. I'm Sam Thompson. I'm the program manager at the US UK Fulbright Commission for UK Scholars, and I want to thank you all for joining us for this first public event in our Across the Pond webinar series, a new and exciting initiative of transatlantic conversations between Fulbright scholars. We're all finding our way through more than a year of virtual exchange. I hesitate to say the new normal, and we've found and come to know as a result of the COVID-19 pandemic. Our vision here at the Commission is a world in which there are no obstacles to learning, understanding, and collaboration. It's therefore very fitting that technology is enabling us to open up new avenues of civic engagement and exchange, not only between scholars, but with all of you, our audience. The series that we've got planned brings together two Fulbright scholars, one from our UK cohort and one from the US cohort, to discuss the intersection of their interests. This evening's event is entitled Scary Science, Responsible Public Engagement with Scientific Research. During the COVID-19 pandemic, we've seen a proliferation of misinformation, and with mass communications and internet usage at seemingly everyone's fingertips, the scientific community has a major role to play in ensuring a responsible and ethical engagement with the public. Demystifying some of the scarier topics in society, think gene editing or ever more sophisticated computing, is a pressing global challenge. And before I introduce our two scholars for tonight, I want to get to a little bit of housekeeping. So this event is being recorded, as will all of the events in our Across the Pond series. So if you miss anything this evening that you want to go back to, or miss some of the upcoming events that you're interested in, you'll be able to find those on our website. And we ask you to engage with the conversation using the Q&A box throughout the evening. So please do that. And at the end, I'll give you the schedule for some of our upcoming events. And so with that, what I'd like to do is move on and introduce our two scholars for the evening. We're joined by Thomas Baker, who is a condensed matter theorist and a Fulbright US scholar hosted by the University of York in the United Kingdom. Dr. Baker graduated from the California State University in Long Beach, where he was supported on the graduate research fellowship while working on superconducting magnetic proximity systems, including a solution to a 200-year-old problem known as the bead on a hoop. Dr. Baker earned his doctoral degree from the University of California, Irvine, where he worked on aspects of simulations of quantum physics for materials with renormalization group, having been supported by the Pat Beckman Memorial Scholar through the ARCS Foundation. As the prized postdoctoral fellow at the Université de Sherbrooke in Quebec, Canada, Dr. Baker published on a variety of topics in quantum computing. In his free time, Thomas has been exploring the history of York and getting back to swimming as the pandemic restrictions lift. I'm also joined by Tony K. Sorial. He's an academic orthopedic surgeon. He is currently the Royal College of Surgeons of England Francis and Augustus Newman Fulbright Scholar and a Wellcome Trust Research Fellow in the laboratory of Professor Farshid Guilak at Washington University in St. Louis, Missouri. He completed his medical degree and a master's degree in regenerative medicine at the University of Manchester in the UK in 2016-17. He moved to Newcastle University to work with osteoarthritis genetics and completed postgraduate diplomas in clinical research and surgery. He split his time in Newcastle between surgical training and laboratory science. In 2018, he was awarded the Royal College of Surgeons of Edinburgh Cutner Fellowship to spend 12 months full-time in the genetics laboratory of Professor John Laughlin to develop a project for his PhD, which he commenced in August 2020. His current research builds on collaborations between Newcastle and St. Louis, and it's based around using human cells and cell lines to understand arthritis with a view of developing new treatments. His work routinely uses CRISPR technology, and in his free time, Tony has been exploring St. Louis with his partner and young son, Helen and Isaac. So with that all said, Thomas, it's really great to have you both tonight. How are you doing this evening?
Yeah, thank you so much for that wonderful introduction, Sam. I really appreciate it, and thank you to all the people at the Fulbright for putting this on. This is, I think, a great opportunity. But yeah, no, I'm super happy to be here. I'm happy to talk about physics and talk a little bit about medicine with Tony. Tony, I guess we picked a kind of a daunting task talking about scary science and things that might send people running in the other direction. But I hope you're up for the task. I certainly am.
Yeah, it's great to see Thomas again. Me and Thomas met a few weeks ago, and we got on really well. I'm really glad to be here today. It's hopefully going to be interesting for people. We are going to talk about some things that might be a little complex, but we'll do our best to digest them down to smaller pieces. If at any point people aren't sure what we're talking about, just write a question in the comments. We're happy to elaborate, but we'll try and keep it at a level that people can follow, and hopefully we learn something, find something interesting.
Yeah. Talking of getting to grips with things and things that we can understand, perhaps I could ask you to maybe explain what we mean when we say scary science. What are some things in your day-to-day work that you interact with that it might be seen in the media as frightening, or that the public might find scary to engage with? If you could maybe start us off with that, Thomas.
Yeah, sure. Yeah. So, when we met a couple of weeks ago, this was sort of the first emergent topic that we thought that should be discussed. Tony, I think, sort of works on the ones that I find most terrifying about the medical sciences, things like CRISPR, which I'll defer the explanation to you, because I'm actually not exactly sure what CRISPR is. But sort of on the flip side of that, away from medicine, there are sort of scary aspects of the research that I work on that when I talk to people in general, or when I'm asked about those particular points of research, people say, well, isn't that kind of terrifying, or won't that destroy the world? And in physics, I think it's sort of the nature of the field makes it so that you're automatically taught to think about very scary things that you don't know anything about. I'm sure that some people in the audience might remember a couple of years ago when they were talking, there was a conspiracy theory that finding the Higgs boson at the particle collider in Switzerland would create a black hole that would swallow the Earth. And of course, this wasn't anything to be afraid of. But so I think that this sort of intersection of things that Tony and I are working on that might have sort of a bad connotation in a science fiction sense can sort of be diffused. So that's why I think we sort of settled on this topic. And so the particular aspects of physics research that I work on that I think are kind of a bit of a mystery for people in general is quantum computing, sort of a radical new way to look at how you design a computer and what potentially scary consequences of that might happen, like breaking the encryption on your computer, or other things of this nature. And I think that's sort of, we wanted to give the audience kind of a safe space to not be so scared about those things. And so hopefully Tony, we can make these things seem a little bit less scary by the end of the talk.
I think what Tom said is correct. Is a lot of these things are quite sensationalist, and the headlines aren't this technique or this protocol or this science could make your life better. The headlines are, this is what happens when it goes wrong. This could be a disaster. So I think at all times when we're doing this kind of research, we have to think about the risks and the potential benefits. And actually, at some point, someone makes a determination about whether something is worth the risk. So the research that I'm working on currently in St. Louis involves using a technique called CRISPR, which some people may have heard of in the news and articles. I'm not going to explain what it is in terms of the term because it's not really relevant, but essentially it's a way to cut the human genome or cut the genome of anything that contains DNA. So it can be animals, it can be mice, it can be fish. The benefits of CRISPR is it's so accessible and it's so specific that we went from a time where we may be able to non-specifically or partially specifically edit the genome over 6 months to be able to very specifically edit the genome in cells in weeks, if not days, with the correct techniques. So the reason CRISPR is scary is because the first assumption of any genome editing research is designer babies. That's always the psychological jump, is we're going to do something and all we're going to do is try and make people designer babies. But actually, there's a multitude of disabling, debilitating, awful genetic diseases that currently are being and will be in future treated by these techniques. And that doesn't necessarily involve creating a designer baby. To give a brief example, recently, there's a disease called sickle cell anemia, where patients' blood cells are the wrong shape. And some people using CRISPR took a patient's cells, edited them to give them the right genetic code to make the right hemoglobin so their cells didn't kill them in essence, and performed a transplant back into the patient. And those patients at 12 months were disease-free. They had some complications, but in essence, that is the power of the technology. And that is where we could be heading. So I think we need to demystify some of the scare stories and think, well, actually, why are we doing this? There must be a benefit to do this. And the benefit is actually there are hundreds of disabling, life-limiting conditions that we could potentially treat with this. And that's what I'm aiming to do with something like arthritis.
So let me see if I understand this correctly. The DNA turns out to be the fundamental building block in cells, and there are specific proteins that I think there's 4 of them or something. And these CRISPR things, they're like they go in and they actually replace the parts of the DNA.
So the DNA is
take one letter and they replace it with another.
The DNA is essentially like a Word document. It's just a list of letters, So if you had 4 letters in multiple combinations over tens of thousands of volumes, that's the human genome. The CRISPR is a copy and paste. You find where you want to target in the genome, you copy it, and then when you paste it, the CRISPR will find this region in the genome. And it comes and brings with it an enzyme, which is the Cas9 system. And that actually cuts the DNA. So the CRISPR is the way that you search the document, and the Cas9 is the way that you edit the document, delete DNA. And it's not as simple as just deleting DNA. We can also now substitute in DNA. So if some patient has a 1 base error, what we call a polymorphism, where 1 single base is changed, that can cause a life-limiting or disabling condition. We can flip that base back to the original so that that patient could be potentially cured of that disease that's caused by that 1 base. So the possibilities are endless. And I know people say that a lot about science, but the Nobel Prize in Chemistry this year was awarded for CRISPR. And there's a reason for that, because the possibilities really are endless, but with caveats that there are risks as well, which I'm sure we'll get into later.
So what do you physically do in the lab? You said that there's an enzyme that deletes the protein, and then there's something else that replaces it. How does it control like which of the proteins are actually replaced? Because if you just say go find and replace for like, you know, a G in a Word document, then like, how do you tell this thing to go
I'm being a little
find the third G?
But
sure.
A lot of lab work is essentially pipetting colorless fluids into other colorless fluids. That is essentially what a lot of molecular biology is. And actually, it's not very glamorous when you're doing it. You're just taking some DNA, which is a colorless liquid in a small tube, putting it on some cells, which are in a small glass device. So the actual laboratory side of it isn't that exciting, the actual doing the process. But what in essence happens is you direct the enzyme with a sequence of 20 bases, which you design by understanding the genome. And when the human genome was mapped, we now know the whole human genome. You can literally look at it online as a PDF, and you can download it. So you can search the genome for certain sites, which will allow you to use this 20 base pair sequence to find exactly the region you want to target. And 20 base pairs we know is very specific in the human genome. So it means that we can highly specifically target the genome. And these guide RNAs, as we call them, they're just an RNA molecule, which is a single strand that can find the area you want it to target, are very cheap. So you can buy this for £20, £30 in essence, which in scientific research is, I mean, I'm sure you can tell us what the cost of scientific research is incredibly large, especially in these large physics experiments and Higgs boson, hadron colliders, that's incredibly expensive stuff. So if somebody says to you, you can specifically target the human genome and edit it for £100, it's life-changing.
Yeah. Well, I unfortunately work on the small potatoes end of physics, so I don't get to touch the big experiments and the big multi-million-dollar ventures. But it's really interesting hearing you talk about sort of all of the little things that allow you to get resolution on this problem, because they're sort of the end product of what we propose in physics. So, you know, if you want to model the chemistry for what's happening inside of, you know, the electrostatic forces that are going on inside of the molecule or something, this is all sort of an outgrowth of high-powered methods for computing quantum physics and understanding exactly how the problems work there. So it's really interesting to hear like these particular things. And, you know, there's a whole bunch of other things in physics that sort of have direct applications to medicine. Not to say that, you know, one is controlling the other. I think that they're working hand in hand, but, you know, things like radiotherapies you know, like proton therapies or chemotherapies or things like this. These are all things that were sort of discovered 100 years ago, and here we are sort of controlling these very deadly things that can be there.
So Tom, you mentioned these kind of things that people 50, 100 years ago thought were deadly and now are treatments. So is there some overlap you can see between some of the things that people now see as scary and how they'll view some of the work you do in, say, 30 years, 40 years?
Oh yeah, no, I mean, I think if we were having this conversation 80 years ago, I think that probably the conversation topic that we would be having are nuclear weapons and how they're, or well, 70 years ago, and how they, you know, are affecting modern life and what we should be doing to control them and how we need to do things. So, you know, really the genesis in physics for why people thought that physics was so important to keep track of and to study was the fact that these huge weapons of mass destruction were unleashed, you know, a while ago, and then there was a huge arms race and all of the fear about, you know, this could bring about the end of the world. But really, when all that stuff was discovered, which was at the turn of the century, notably by Marie Curie and other people, the focus was sort of, how do we study these subatomic particles and how do we control them for things? So one of the first things that they did was they took an X-ray, and so this is like, you know, some very fundamental piece of everyday hospital life is taking X-rays to see broken bones instead of, I don't even know what they would diagnose people with before they had X-rays or how they would do this. Well, I'm sure if you press it, it hurts, but you know, having the X-ray probably helps you to be a little bit more specific about how to treat it. But you know, it's sort of the way that the story is told. There's sort of one step forward, two steps backward. It wasn't that we found these things and then we immediately started applying them in hospitals. It was like we found these things and then we were using them in paints. And then so there are horror stories about people who would like lick the paint brushes and, you know, they'd get mouth cancer or something. And then of course, when the war came around, they were like, how do we use science to sort of engineer these terrible and big weapons? And so Einstein had this famous letter to Roosevelt, FDR at the time, and he said, you know, you really need to look into this because this could potentially be very bad. And so if you understand that the force that is holding the nucleus together, if you split that, this can unleash a lot of energy. But you know, there's also a lot of benign uses. There's nuclear power, which has another spotty record. But a lot of, you know, cancer therapies and things are highly reliant on knowing the knowledge from nuclear physics. So it's really something where I think there's a lot of good uses for things, but I think that really one of the things that is the best protector against some of the bad uses, which are very obvious in that context, are people knowing about it and being well informed. So I think that's sort of a motivation for being here and having this conversation, I guess. But having, certainly in a democracy, having the voting public understand the capabilities and limitations of these things is another one. I'm sure that I'm sure that if we were doing this conversation 10 years ago, you would have probably talked about stem cells, right? And you know.
So it's interesting because these things do go in cycles, and as you said, every time there's a new ethical dilemma, and then the science moves, and the science moves so quickly that sometimes the ethics and the legislation take time to catch up. And I think the important thing to be aware of is with all of these things, well, particularly in biomedical research, I know we're going to talk briefly later probably about the ethics of theoretical work, but in biomedical research, all of these studies, investigations, these techniques require ethical approval, and they can't be undertaken without ethical approval. And the process of ethical approval is a long process. You have to write a full application explaining everything that you want to do. You have to take it to a committee where there will be scientists, there'll be lay people, there'll be members of the public, there'll be people who won't be scientifically minded. And at that point, if the science is not ethically approved, it cannot proceed. Now, there's caveats to that, which I'll speak about later, where some people have conducted science without ethical approval, and that's one of the reasons we need to be very careful with something so powerful. I know it's probably a silly quote, but in Spider-Man, I think he says, great power, great responsibility, something along those lines. Yeah. people don't follow the rules, which have been internationally agreed, then that can be a real problem. I think most of the time people have positive intentions. They want to advance the science because they think they can make people's lives better. But it is essential that we always have ethical approval, that we always have patient consent, and that's informed consent. If the patient doesn't understand what is being proposed, then they cannot give consent. So these are benchmarks of good scientific integrity, and particularly with research like this, which we'll probably discuss a bit later, but there's two lines of genome editing, and the one is editing cells that have differentiated and cannot become a fetus or an embryo, and the other line is embryonic research, which is where editing a cell could be passed on to the child's daughter or son, for example, we need to separate these two out because they're two different questions. And what we call somatic cell editing, editing cells that are in an adult patient, for example, are very different to editing an embryo. And for that reason, there is more ethical considerations and there's more legislation preventing that. So for example, in the United States of America, you can CRISPR edit an embryo, but you cannot implant it. And you cannot be given public funding. So the NIH will not currently fund embryonic CRISPR research.
Is that true in other countries too, or is that just specific to the US?
You can edit an embryo and you cannot implant it. In fact, globally, I don't know of anywhere that you can implant a CRISPR edited embryo into a human being. However, which we will come to later, somebody in China did do that. And that's one of the major controversies of this research. That was a kind of stop moment where there was a lot of uproar, so rightfully so, that somebody had taken that step without consideration of the legality, the ethics, the consent. And we can discuss that in a bit more detail, but that's kind of the worst case scenario. And actually, I think we need to, on balance, say we've cured conditions with this, and we're in late stage clinical trials of curing conditions with this technology. And actually, that person was somebody who went outside the scope of legality and ethics. And that is not what people should be afraid of, because in the millions of people using this for good research, one person went rogue and did something that was illegal and was unethical and would not have been ever approved at this current stage of the research. So I think we have to not throw the baby out with the bathwater and say, well, actually somebody did something wrong with this, we should just abandon everything, because the potential for positive impact on people's lives is huge.
It's so interesting. Yeah, go ahead.
Yeah, ask about, and take a step back perhaps, because you talked about some of the ethical rigor that goes into this research before we even start on it. And I can sort of imagine why, in the same way that when we started, we talked about you hear the scare stories before you hear the science, because it's what sells newspapers and gets eyes on TV sets. But why is it that we as a public aren't more familiar with this process of ethical rigor that goes into, for in your case, biomedical research? Because I feel like that would put a lot of minds at ease if we knew just how much work goes into this before anything even starts in an applicable sense. So is this something that you think the institution, say a university or a hospital where research is being done, has a responsibility to share with the community around it? Or
so in the last few years, I know there's some people here today actually who have worked with me before on public engagement. There has been a swing from scientists thinking, this is great, this is a brilliant idea, we'll do it. And somebody saying, yeah, okay, I agree with you, here's £1,500,000 to do that for the next 5 years. Most of the funding bodies now will require public engagement. And public engagement should not be tokenistic. It should be that you've actually engaged with people. And because the long and short of it is, if you develop a fantastic treatment and a member of the public says, don't touch me with that, it goes nowhere. So I think the amount of awareness of these procedures is increasing, but I think it tends to target a quite niche group of people who are interested already. So a lot of the people in our public engagement panels are people with a condition. So for example, with osteoarthritis, people are interested to engage with osteoarthritis research, but that might also only select people who are 60 plus. So suddenly you're not engaging with younger people because your condition is picking out who is actually interested to talk to you about it. I think people are sometimes a bit intimidated about reading something scientific. And the reason we now have to produce in our grant applications lay sections, that's exactly to help us to distill the information so that a member of the public who has no scientific background or minimal scientific background can understand it. And I think in the next 15 or 20 years, hopefully we'll see that events like this and the process changing, where scientists have almost been forced to undertake public engagement and have realized after that it's beneficial to their research. That should hopefully shift the balance. The concern is with something like this, the government will always be pushed by public opinion. So public opinion is that this isn't what we want, this isn't ethical, then unless there's a very strong scientific argument for it, or the argument has been presented correctly and people still say no, then it won't proceed. I'd be surprised if when people understand this properly, genome editing and the potential to treat disease prior to any embryonic work, they wouldn't advocate for it, because there is some fears and it can be scary, but actually the amount of testing that is going on in this is we're talking 15, 20 years before probably any large scale drug treatments with CRISPR, those kind of things. So I think there's going to be a lot of work to be done before then. And when that is presented to the public, I would hope that they could see that the benefit would be larger than the potential risk, particularly in somatic. Embryonic starts to become a bit more of a gray area, but editing cells from a patient, returning those cells to a patient and making them healthy is a no-brainer in my mind. As long as people understand the process, they're happy with the risks and benefits, they give consent, and it's ethically approved, there's no reason we shouldn't be looking to do that.
Sure. And Thomas, is there a similar process in your field when it comes to approving work and communicating with the public about it? Is that something that we're seeing on your side of things too, or is that completely different?
I had to apply for some funding very recently, and in the funding applications, this was sort of the first time that I was looking at funding like this that was more interdisciplinary. So they'd already had many applications from biology and from medicine where you need to keep track of these ethical concerns. So I was presented with this big sheet of, are you using human subjects? Are you using cadavers? Are you using any of this? And it was really a very easy sheet to do because I just marked no. And pretty much everything in physics, maybe some areas of biophysics might veer into this or something, but pretty much every area of physics is has no formal ethical structure. There's no formal system set up. We know that there could be awful consequences for things, but I think that the focus is a lot more on, can we understand everything about them? Not necessarily educating everyone in the field about them, but can we understand everything about them to the point where we know all of the consequences? So Tony, I think, has done a very good job of illustrating things that can appear on a timescale of 10 to 20 years and might, horribly corrupt, some genomes. So you really need to be careful about how you're applying these things and making sure that everyone is consenting. Physics has a much longer timescale over which things develop. And this could be 100 years historically for things, but it's also sort of, computing, I think maybe is a very generic and benign example, because it was sort of hard to predict how things would go wrong, like mass disinformation or social media when it first came out. I think that sort of one of the benefits in physics is that you really have no idea whether you're going to have in-home electricity when you're studying things at a very fundamental level. Having said that, there are a couple of things that crop up very early on in research that can sort of tell you whether things are going to be should be carefully looked at. And so in quantum computing, it's this fundamentally different way to approach how we make a computer. So your computers and everything that we're using to sort of communicate right now and during the pandemic, it's all reliant on pushing electron charges around. So I think this sort of makes a nice picture in everyone's head, because in your high school classes, hopefully you learned about electric charges, and there are just very advanced ways to move these things around in a circuit, and that allows us to send signals and have computer monitors and turn on the lights, for example. Now, the problem with having that is that by pushing these charges around, you make a lot of heat. And so it turns out that since 2005, even though we theoretically could make a processor that's smaller and as Moore's law advances, in practice, the heat density that exists on a chip goes up and up and up. And so it gets harder and harder to actually increase the processor speed in a regular computer unless you improve the cooling, or you make another processor, or you do a lot of other fancy tricks. Now, what quantum computing proposes, and this is something that goes back for at least 50 years, is that you re-understand how you're moving information around in the circuit. And instead of using the charge of an electron, what we use are the fundamental properties of quantum physics. So as soon as you start to learn about quantum physics, there's a bit of a scare tactic that happens, and they say, well, we don't really understand anything and everything is kind of weird. It's all entangled is the key word there. And I think I'll just skip an explanation of that. But it's that things do not necessarily have a definite state that they exist in, and that they can exist in combinations of these states. And if you can manipulate some unit on a quantum computer that exists in a superposition of these states, then in principle, you have a completely different type of computer. You know, a linear, for example, a linear combination of the charge being there and the charge not being there. This would be something that is allowed under the solutions in quantum physics. And the idea is that if you remake the computer like this, then I think one of the first fields where this was captured the popular imagination was computer science. And there was a guy in the 90s called Peter Shor, who came up with an algorithm that does integer factorization much, much faster than any known algorithm that we have on a classical computer. So what happens when I send a message to you through email is there's some very large integer number that is transmitted with it. And this is the simplified picture. But if you already know how, you know, a set of numbers, and these are called prime numbers because you cannot further divide them by another integer. If you have the set of integers and you multiply them up and then get this big number, that essentially constitutes a code. So what it basically means is that if I've given you those numbers beforehand, then you're able to remake the code. And you know, I'm skipping a lot of details here, but this is the basic process. Then you're able to make a large integer out of that. But if you wanted to intercept this code and then try and decode it, like some spy is out there trying to, you know, decode our message about, you know, saying hello or something, then what they would have to do is they would have to do the reverse process. And so while it's very easy for you to multiply these numbers up and then check that they match the integer, if you want to start from the integer and then start dividing by numbers, it turns out that this is very, 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 very difficult to do on a classical computer. It would take you several years or decades in order to do this. Now it's proven that this quantum algorithm can indeed do that reverse process very, very quickly. So if you have intercepted a message and you keep it around for a couple of years until we get down the road with quantum computing, then in principle, you could just throw that number onto the quantum computer, run this algorithm, obtain all of the prime numbers, and then be able to read the message by decoding it according to whatever code this is. And this is sort of, you know, I think that this was probably the genesis of why quantum computing became important. It was an example of an algorithm that you can't run classically, that can do something that you can't do classically, and it also has national security implications. Okay, so this is like, you know, this is obviously something that we should fund and that we should understand and that we should be able to do. So I think a lot of progress in that has developed over the years just because of sort of the fear of the unknown, which isn't necessarily a bad thing, and I'm sure Tony would sort of agree with this too, but fear of the unknown is not necessarily a bad thing. And so, you know, if you see something scary in the media or something like that, it's just to get your attention. And I think what they don't do a very good job of is sort of bringing out experts and then making things more digestible for the audience. And sort of to answer your earlier question, like what's the best way for the public to sort of engage with this? Honestly, I think, you know, that experience as a professor that you have, not necessarily going to an outreach activity, but when you're teaching to those 18 to 30 to 100 students in your seminar room, that's really the time when you have the right amount of time, a long time to tell the students about, you know, what is physics? How do we think in physics? How do we actually do things? How does the world around you work? That's really the time when we should be thinking about doing a lot of outreach with students, and that's when we should be thinking about how do we educate these people so that they can be responsible citizens later, not necessarily shove them out the door and then hope that they can learn about the next new thing later. That's sort of our job. The job of the public is a little bit different, I think.
I'll just echo that. I think, like you said, the real risk is that you just select out a certain group of people who are already very interested, and actually we need people who are also not particularly interested to understand these things, because at the end of the day, the majority, these things may be applicable to the majority, not just the minority who are interested to understand. And techniques such as this like you said, if it's a national security thing, it may directly affect the security of people in a whole country if their government were to be involved in this kind of work. And actually, if that makes your country where you live and you believe you're safe more susceptible to attack or less susceptible to attack, cyber attack, for example, then that's something that the public should be aware of and understand. I don't mean to understand the minutiae of the details, but have an awareness of how these things could potentially impact their life and how these things could have direct and indirect, positive and negative consequences. I think people need to understand that, because at some point there will be a reckoning on a decision whether this type of research, both genome editing, quantum computing, things like that, will proceed to the next level. And that's where the public will be making that decision. Governments just make decisions based on the public. So in essence, public opinion will make the decision rather than politicians most of the time. I won't say anything like that.
Certainly, I think that there's a bit of an expectation, and in some small doses, I think that this is very healthy. But I think that there's an expectation that all of these things can be made very easy and very understandable by people. And this is something that even though special relativity has been around for 100 years or so, or more than 100 years now, it's still something that is not, there is no song and dance that you can do and then have someone turn around and then fully understand that topic. Whereas I think, with using a Word document, I thought your example earlier was pretty good. If you sort of, you can make a kind of an entertaining presentation in order to tell someone how to use a Word document, and this can be very useful. Or with the financial crisis more than 10 years ago, they had some really nice, good presentations of like, oh, this is why this is happening, and this is why it affected everything. But I think that there are some things that sort of are almost hindered by having an easy presentation. And if there's a large expectation that the audience doesn't have to do any work in order to sort of fully understand quantum physics or something like this, I think that this is a bit of a danger, and it can lead to leaps that might not necessarily be made.
And do you think we risk almost losing some of the gravity of these subjects if you make something easy to understand? Does it, we're talking about demystifying kind of the scary side of these things, but if you make it easy to understand, you almost diminish potential consequences of the research as well. Is that a risk here too?
Well, the quote that comes from physics on this is from Einstein, and he said, make everything as simple as possible, but I think everyone leaves off the second half of the quote, which is, but no simpler. And I do think that sometimes things are made a little bit too simple, or a little bit too pulled back, a little bit too base. I hesitate to curb anyone's enthusiasm for trying to make things simpler. I think that has usefulness and is good. On the other hand, I think I think that the right antidote for that, though, is to say, if you're really interested in this at all, even in some little way, it shouldn't be too hard for you to get the resources, to get a little bit of time to actually understand that. And so I guess the main message that I'm trying to get across is, like, if you want to take a college course, you shouldn't be scared out of learning the deep fundamental, the deep core of it. And I think in physics, we have a little bit of a problem with doing this. But you shouldn't be scared out of thinking that you can't do it, or that it's too complicated for you. You should be provided with a safe space to say, okay, you can learn it. You probably have some weird way to get to being an expert level, but try anyway. And if you can get that far, then that's probably how you need to spend your time. Not necessarily expecting that everything's going to come to you and that's going to be super simple. And I think that that's sort of the healthy approach to this, is that we should be providing opportunities for people to learn these things, not necessarily scaring them into thinking that these things are too complicated or too tangled for them to understand.
If I could expand on that, I would say, I'll give my own very honest assessment, is actually when I first started doing this, I think I underestimated the ability of the lay public to sometimes understand this research. And actually sometimes you can oversimplify it. And the people that I've worked with, actually, they work in groups, public engagement groups. I know some of them here today, they read papers, they probably read more papers than me. So suddenly coming in there saying, oh, there's a word processing, like, oh, you're talking about DNA, genome editing, and they've read around the topic. And actually, people who are interested and engaged will make effort to go and read around these topics and actually understand the science to the best of their ability. They may not be able to understand the molecular level or even what's done as a physical process in the laboratory. And actually, who cares? Why do you need to know what happens in the laboratory as long as you understand the risks and benefits, how it works, and the potential implications to your life? You can make an informed decision. And at the end of the day, people don't need all the information. They need enough information to make an informed decision whether they think this is something that should be applicable to them, and probably for most people, their children, because by the time their children's generation comes around, that's likely to be when genome editing technology is in clinical use of trials and more routinely used. And I think people should be thinking about those kind of things now, because actually, I think we're only one generation away from this being a routine treatment for many things. So it's something that, having spoken to people from the public with sometimes no scientific background, they can digest, they can understand, as long as it's presented in a way that is not patronizing. Actually, that's the best word for it. Just, this is actually information. I can expand on this information, or I can give you less information. You direct me, rather than saying, I'm going to give you no information or all the information, and it's up to me. Actually, what you should be trying to do is take each person that you engage with and say, what is your level of knowledge? Can I cater this to you so that you have enough information to make an informed decision as to whether this is practical, reasonable, or ethical in your mind? That's what I see it as.
Great. Yeah. Are you guys happy to take a question from the chat?
Absolutely.
All right. So we've got a question here, which is, how do you tend to think about some of the consequences of the research that you're doing? So, on a daily basis, some of these consequences that you talked about can be, pretty scary. Can, I imagine, stick in your mind. So how do you tend to think about those whilst actually doing the research as well?
So I'm happy to go first on that one. So it's challenging because actually, on a day-to-day basis, the work I'm doing is looking at for example, a cell line. So you take a cell from a human, you make it so that it can grow infinitely, and you target that line. Naturally, when you're doing that on a day-to-day basis and trying to grow, for example, a tissue from a stem cell, you're not thinking about embryonic stem cell editing in 20 years' time. You're thinking, I'm trying to prove that this works in this situation for this disease. And only when you sit and start writing or reading and start writing grants, that's when you think about the bigger picture and say, well, actually, where is this going? Is this going to be something that is of ethical concern? And currently the work I do is ethically approved, is legal, and there isn't those concerns on a day-to-day basis. I don't stay up at night thinking, oh my God, embryonic genome editing is going to end the world. But because it won't as well, that's the other thing to say. But you have an awareness. You have an awareness that there's something bigger than you and more important than you, and actually you're a small cog in the machine looking at one disease and one type of cell, trying to make lives better for people with a condition, understanding that there is broader scope of that, both in your own research and when we start to think about embryonic research, a much broader scope for that kind of treatment. But we're essentially trying to cure a problem in a lab.
It can certainly be demoralizing to, if you focus on the negative things, the negative endpoints of your research. It can also be sort of intoxicating when you ignore them. Like if you ignore, the fact that if you ignore some negative consequence of things, you might be overly optimistic about some direction you're pursuing, and that can be bad too. Typically, though, I tend not to think about the end stage consequences of what I'm doing. It's much more useful to think about, well, this could be optimistically used to predict some new material, or it could be used to, I don't think we've discussed it yet, but machine learning for new materials. This is something that I had a paper on a couple of years ago. And the focus on that was, well, this could really like solve all of these things, and so I would say that 9 times out of 10 you do focus on the positive things. There are physicists who sort of work more closely with the more gray side of things. Their research has direct applications with explosives or with weapons, or I remember running into someone that was thinking that the machine learning algorithm that they were working on was going to have some ill consequence if it got into the wrong hands. And I had to calm them down a little bit. But typically in physics, because there's such a long lead time on actually generating something that would potentially have an ill consequence, you have a much bigger buffer with your conscience when you're actually doing the research.
I think that actually leads really nicely into our next question. So do you have particular ethical lines in your work that you're drawing a firm line on, or that you won't cross as the work goes on?
Yeah, I've been very lucky to avoid a lot of them, but there are parts of it that I tend not to dirty my hands with. I honestly, I would say that in physics, the biggest ethical challenges are sort of interpersonal, and because nothing is regulated, you can wind up in a situation where it's like, oh, should we be doing this, or should we be doing that, or what's the best use of our time, or should we be allocating resources in this way? These are sort of the big questions. As far as the actual research goes, I would say that most of the ethical questions that we try and avoid are, are you misleading the audience by writing a paper like this, or are you are you making some erroneous statement that might mislead people? I would say that that's the biggest challenge that we try and avoid in physics. That's where most of my focus is, and we try and avoid that essentially.
I think from our side of things, it's not really for us to make the decision. So I cannot decide what line can or cannot be crossed. The public and the government and the ethical approval committees, they make the decisions about what lines can or can't be crossed. And those decisions, I don't want people to think those decisions are ever taken lightly. These are things that after what happened in the Chinese affair, basically, I'll talk briefly about that. So in essence, a Chinese scientist went against his institution's ethical approval, and he generated 2 or 3 edited embryos to try and prevent HIV cells from getting HIV by deleting a certain gene that we know allows HIV to enter the cells. Without approval, he implanted those embryos into 2 women. One woman had twins, which were born prematurely, and the other woman had 1 child. Now that was completely against all ethical approval, all international approvals, and was completely illegal. And he's now in prison in China for 3 years, which I think was the right thing, to be honest. That put a brake on the community, and it shouldn't need to have come to that. But I think people were very much like, we need to issue a consensus that this is not acceptable at this point in the research. And I don't think anybody should ever think that they're bigger than the public, the government, the legislation, and the community, and go beyond those lines. Those lines are drawn across international consortia by people who have realms of vast experience in these things and based on public opinion. And any legal, ethical line should never be crossed if it's been laid down by a approved body. So there was no reason that should have ever happened. And the risk is when things like that happen, actually, it sets the research back. Because if that happened in 5 years' time with the correct approvals and the correct legislation in place, and we had more research to show that that was safe, then we wouldn't have to have conversations like this, where now we try and justify this because of a bad actor behaving in a way that was completely legal. So I come back to the thing with great power and great responsibility. You have to understand that this is something that could essentially cure genetic diseases that kill children in childhood and infancy. This is not something to be ignored and thought, oh, it's just a small thing, you're just pipetting some colorless fluid in tubes. The potential is really vast, and that has its own burden of ethical weight that you can't ignore. And that is why these decisions aren't left to scientists, because a good scientist will want to do something novel and advance it and get to the end point to be the first person there, because there's prestige, because there's grants, because there's work in that, and actually because they want to make people's lives better. I'm not playing that scientists who want to make people's lives better. But the risk is with that merit-based system that people can be driven to do something that they may think is fine, but is not. So that's why we need broad legislation. We need international consortium and consensus opinion that the line is there and we do not cross it until that line moves. And that line only moves when we know it's safe for it to move.
It's so weird to hear that you have like a formal structure for these things in medicine, and that makes a lot of sense, because it really is sort of a harm that you do to someone else. In physics, in this more sort of Wild West culture that we have, it's more a little bit more direct when you have a violation of something. Every once in a while there will be some huge scandal that appears, and so the two that come to mind are around the turn of the century, around the year 2000. There was a guy who was working at Bell Labs, and he said that he had basically made a technological advance with materials that would have drastically changed modern life, like room temperature superconductivity type thing. And he got into the top physics journals every week for a year, because no one had caught on yet. And he was a little bit aloof, so he was just riding that wave of things. And at some point, someone noticed that the noise that was drawn in two different graphs were the same, and they couldn't account for why this was. So they asked about it, and it sort of unraveled the whole thing. And he not only did he get his papers retracted, but he got his PhD stripped away. So it's not, that in and of itself didn't really hurt anybody. It just caused a lot of people to waste a lot of their time when they could have spent it going in another direction, and just sort of tainting the scientific record in a very serious way. But that was taken. That's the shining example in physics of when things go wrong like that. Now there is another more recent example, which is slightly more honest. But there was a version of quantum machine learning, so machine learning on a quantum computer, that was used for 20 years or so. And then a very bright physicist, Yuan Tang, came out and said that actually there's a classical algorithm that is better than this. So these quantum algorithms are not as good as you think that they are. And weirdly, in the literature, even as far back as 2004, there was sort of math proof saying that this wasn't realistic. So it's a little bit weird how it was allowed to perpetuate through the literature. But this caused a big kerfuffle. It caused a big deal. I think one of the scientists who was on that paper, who was on the original one, had to take a leave of absence. I would think that was more related to some other things that were going on. But in physics, it's a lot more regulated by the mob. I hate to say crowd, but it's more like the mob here. And so, but sort of the same ends, I suppose.
I do think there's an element of that as well, because the scientists who understand the most about this will directly tap in to those international consortia. So there is a bit of self-regulation, but that self-regulation is then moderated at a higher level by legislation, by ethical approval. So something that a group of 10 scientists think is not ethical would not even make it to an ethical panel, if you see what I mean, because people say, well, you can't do that. If somebody said, no, I'm going to take it and do what that Chinese scientist did, and so I'm going to plant a CRISPR edited embryo into a child, he wouldn't make it out of his group, let alone to an ethical approval. The interesting thing about that case was he actually had collaborators at international institutions, including in the USA, who were named on those papers and were part of that research, and it's not been clear yet what the role was. But people who are established professors in American institutions were involved in that research to some degree. We don't know the full degree, and that shows you that even somebody who is regulated, legislated, understands the process inside and out, can be drawn in to something that might seem like it's going to be revolutionary, but may also be not the right thing to do.
That's right. Yeah, and that's probably a line that should be further clarified. Is how should, because in this example of this very famous cheating scandal, the advisor suffered no consequences essentially, so I think that's certainly a line that should probably be clarified. But I don't want to give the impression that science is just dominated by cheaters and false things. There's also a lot of good work that happens, and that goes through. So it's wonderful when it works, and it's just very, very exemplary when it goes off the rails like this.
So our time has actually flown by, and we are facing down 6 p.m. quite rapidly. So I suppose, is there anything that you think that we've missed that is really important to this idea of scary science and responsible public engagement that you think we should actually take a couple minutes to talk about anything that maybe we stopped on briefly and would like to revisit, or that you think actually we really should have devoted some time to this, and if people are interested, they can go and read on it. Like what have we left out?
Sam, I'm happy to answer this. There's a question.
Oh, there's a question in the chat as well. Yeah, actually, this looks interesting too. So let's do this as our final thought for the day, which is how do you rate the chance of science communication in your fields in competition with the spread of conspiracy theories and related fears?
Yeah, so I go ahead, Tony. Yeah. So I think that my answer for this sort of it goes hand in hand with both questions. I think that in terms of disseminating honest communication about physics, or really in any field, it's very, very important that students that are upcoming through the system and upcoming through the educational apparatus that we have, that they're given enough time to think safely and think through things without being influenced by fear. I'm not so sure that the popular attempts to disseminate science sort of at the late stage, as popular science documentaries or things like this, these should never be viewed as a substitute for actually being patient and actually learning the things longhand. So in terms of spreading against disinformation, I mean, there's been so much disinformation about quantum physics and about quantum computing over the years. It's really a losing battle. You really have to rely on the experts to understand that they know what they're doing, and that if you want to follow them, then you have every right to request that you get, sort of a safe space, but you're still held accountable to being right in that instance. So I think if you're like a high school teacher, or if you're a high school student or something, really as the general public, we should be supporting even those sort of formative years. And I think maybe the aspect of this that we didn't touch on is that this leaky pipeline of maybe only getting one kind of gender or one kind of race to come through the scientific process. This is something that we should really hone in on. So if you're really worried about disinformation, I think that those formative years of education and even things like the Fulbright with cross-cultural collaborations, these are the things that you need to support in order to make sure that you have enough knowledge to combat disinformation. Having more people who know things combats disinformation, not necessarily better compressed versions of the full thing.
Yeah, I would agree with that. I think, like you said, it's a real challenge, because even with something which has been so globally prevalent like COVID, we still are struggling now to vaccinate people. And that kind of shows you that even with something that people can see in front of them that is directly threatening their life and the lives of people around them, it's still hard to overcome that. I think we're so early in the Crispr research that hopefully it will become part of school curriculum. So I can't see how this doesn't become part of kind of like high school learning, and people need to understand what this is and how it works. I would just make a plea really to people to actually, this will affect your life. There's no two ways about it. If you're alive in the next 15, 20 years, this will cross your path, your family, your friends, your own children. It's something that will at some point be presented to you and say, would you consider this? And I would just say to people, if you can make time in this busy world, particularly in a pandemic, to try and attend things like this, try and, like Tom said, it can't always be, we can try as much as we want to give people information, but actually people generally are more interested when they find their own information. They take a source and say, well, that's really interesting. I'm really interested to learn more about that, and go away and look at it in more detail. That's how people learn. People don't learn from listening to someone like me saying, oh, this is really interesting, you should be interested in this. And when people are genuinely interested and they go away and look into these things, they will understand them better. And I don't think, as I said earlier, we shouldn't patronize people. You could read a scientific paper on CRISPR and make sense of it as a lay person with a bit of knowledge of that the DNA is a string of letters. You could start to understand things like that. I'm not saying go and read Nature papers on CRISPR genome editing, but there is a lot of resources. We're going to share some resources, I believe, and there's a paper which it's quite long, but it's worth a read, by a professor of law who wrote basically about the whole He-Jiankui was the scientist's name, what he called the He-Jiankui affair, and basically the risks, benefits of genome editing and how we have to always think about those, and why this was such a poor use of the science, legally, ethically, and scientifically. I think the main thing is that people be aware that this will probably be something that will be relevant to you. And as human beings, we are inherently selfish. We're interested in things that are going to affect us, and this will affect you at some point in your life. If you're alive for the next 20 years, this will appear in your psyche. It will be something that the government will be talking about. It will be something that may make your life better, and probably will make your life better if you suffer from any multitude of conditions. So it's something that people should be interested in because it will directly affect them. And for no reason other than that, I think people should be interested.
Great. Well, thank you so much for being here, both of you. It's been an absolute pleasure to just get to talk to you about this and hear your conversation. And thank you all at home for tuning in, whether that's live or whether you're watching this pre-recorded. I want to let you know about some of our upcoming events. So on the 6th of July, which is next week, we have our next event where we're inviting 2 more scholars to come in and talk up on the theme disease detectives. They'll be talking about tracking and modeling infectious diseases. After that, on the 13th of July, we have 2 more scholars talking about tackling trauma. And on the 20th of July, we've got another pair who will be talking about community storytelling and cultural institutions. So if any of those sound interesting to you, please do sign up and come along. The event pages are on our website, so you can sign up for those in the same way that you did for this event. And if you want to keep up with things that we're doing, you can always find us on our website. You can follow us on Facebook, Instagram, LinkedIn, and find us on Twitter at US UK Fulbright. Once again, thank you, Thomas. Thank you, Tony. It's been absolutely wonderful to be here with you tonight. And I hope everyone has a great evening, great weekend, and we'll see you all next time.